It's a stone mill.
Now, the real interesting question is, what does the second derivative test have anything to do with why concrete or bones tend to fracture diagonally, or how correlation between statistical quantities work, and the mathematical description of the rotation of a rigid body? Let's start with the two-dimensional function and choose a point on it.
Okay, stop. Most of you don't have any goddamn clue about anything at all when it comes to that. So let me get two things real quickly here. We're in one, but it's a set theory argument. Let's get to a point where we can actually do it well. Oh, no, that's not what I want to do. I want us to have do. We're picking a point on a two-dimensional plane. That's what we're doing right now. Both of those are two-dimensional planes, by the way. SU2, SU3, something like that. So we picked a point. Bang, we're in that point. There was other points there. But we're in that point. We're picking a point on a two-dimensional plane. The problem with most people in the way you understand that is it's not always what you think it is. To start here in the middle of the process of programming a block would be weird. It's not the way you set up that equation. But at the same time, what I'm doing is an overall book or the process of laying in the first derivative is a two-dimensional plane, and I'm picking a point. That is hydraulic oil in the saws, and when that cycle happened and where it happened. So essentially, I've picked a point on a two-dimensional plane. Now, before I go back to it, I want to talk about it in another form. This is the second derivative. The second derivative I want to apply to this is that there's any position you can start into this. When you come in as a ground guy, there are a lot of second derivatives. The main derivative that you're going to watch is to pull these bunks and lay them down inside of there. That is the primary task that has to go inside of whatever bar metrics that's more important than anything else short of a fire or electricity, spooky monster, Montauk monster running in the building. This first order derivative is made up of second set theories and set theories. But the idea is you could start from a ground guy hand picking rock out there cleaning and doing that stuff, and here's the checklist of the dipstick and the safety sheets. That's a version of it. We can do it as a guillotine operator inside of here that you're working the saws and how many pallets you're putting out. That's a variable of it. We could say it's the training boss's game of seeing them how to do a thing on certain lines and equations, saw programming, thermal in the block, or Sawyer stuff. Any of those are the first point on a two-dimensional plane that you're looking for.
Unsurprisingly, the zeroth order Taylor expansion at this point simply gives the function's value.
So P here, again, we've been talking about it before, P0 is LZ. This is standard. There is no numbers to this at the base of that order. And for sunshine reasons in Earth, that's always that. We're saying that we understand that there's a gravitational to that, and any other force is me throwing the ball. And that's how far it'll go, or me walking up a hill. The distance is unknown here once. And in this case, because it's soil, it would, but ground isn't that. So as long as it's uphill or downhill, any evolution this hill twice will give us some mass difference, spring force, or arbitrary nature of the coronosphere to its core, and here it would just be the outer photon.
Slightly more interesting is the first order expansion, which involves the partial derivatives with respect to each coordinate direction. Geometrically, the first order polynomial represents the tangent plane, much like the tangent line in one-dimensional case. We're about to get really cluttered here, so let's use bold letters to represent vectors. Then, the tangent plane, or the first order expansion, is given by this formula.
Roads being chaos theory.
Now, for the second derivative test to be meaningful, we need both partials to be zero. Now, much like in one dimension, the second order expansion in two dimension is the tangent paraboloid at the point. And it depends on each of the second derivatives. If you are wondering why the mixed partial term isn't divided by 2 factorial, unlike fxx and fyy, it technically is divided by 2. just there are two equal copies of them due to commutativity of partial derivatives. Now, just like how the gradient captures all the information about first derivatives, the second gradient captures all the information about second derivatives. This matrix is also called the Hessian. If you want to continue to third derivatives, it becomes a rank 3 tensor, so it does become increasingly disgusting to work with. But luckily for us, all we need is the information about second derivatives. Zeroth order term just affects the height, and the first order terms all have to be 0 for second derivative test to be meaningful. So we really only need to study the second order expansion, or equivalently, the second partial derivatives. Let's label the Hessian matrix as H. The Hessian does indeed provide a complete picture of the function's concavity, but it's quite unintuitive on its own, so we typically extract two important scalar quantities, the determinant and the trace of the matrix. The determinant is precisely the discriminant for the second derivative test. And the trace, if you're not familiar with it, is the sum of the diagonal entries, which in this case is the Laplacian. We will eventually understand what these quantities represent. We mentioned earlier that we only need to consider the second order expansion. If both directional concavity is non-zero and with no mixed terms, there are just three possible cases. Either it's concave up in both directions, or concave down, or it has both up and down, so it makes a saddle shape. Now, in this case, the determinant simply is the product of each directional concavity. If they have the same sign, it's a maximum or a minimum, and if they have different signs, it's a saddle. To determine whether it's actually a maximum or a minimum, we could use the Laplacian for the first two, which is twice the average concavity. But unlike using just one of the second derivatives, as most textbooks teach, the Laplacian gives us